Hello, I want to discuss this coin flip algorithm. The theorem is this coin flip algorithm is 3 times competitive against some adaptive online adversary. So this is the theorem and we want to prove it. So coin flip algorithm is 3 times competitive against the adaptive online adversary algorithm. And let's have some suppositions where so C opt is the optimal cost and CF is the cost due to coin flip algorithm. So C opt is the cost of fixed online algorithm and CF is the, so we are supposing fixed online algorithm is the optimal algorithm. So this is the cost of optimal and CF is the cost of coin flip algorithm. And we define this potential function phi. Phi is we suppose phi is 3 times d. D is the size of the page and into the distance between PCF and POPT. So PCF is the node where coin flip algorithm starts and where coin flip algorithm puts the page, and COPT is the place where this adaptive algorithm puts the page. And this is the figure, and in the figure B asterisk is the place where the request occurs, and this is the PCF and this P opt with the distance is A, this distance is B, this distance is C. Okay, now let's start. Here basically we divide the whole algorithm into the two parts. In first event, what happens is request comes to B asterisk, so request comes to this node. Then what this CF and this optimal algorithm does is it serves the request. Then after this CF algorithm, coin flip algorithm, may optionally move the page. Then in second part, this optimal algorithm may optionally move the page. So let's make a note. If you see in event 2 there is no, so in event 2 coin flip algorithm does nothing, so it's only optimal algorithm who is doing some tasks. Okay, so what now we have to prove is is the expected value for this coin flip algorithm cost plus the change in potential, the difference in potential, is less or equals to 3 into cost of optimal algorithm. So that's what we have to prove. Okay, let's begin. So what we do is first we make a proof for part 1. Part 1 or event 1. So in this part 1, what we are doing is we are simply comparing the cost of this offline algorithm serving the page versus the overall cost of the online algorithm. Because because in event 1 what offline algorithm does is it simply moves the page but the online algorithm, that is the coin flip algorithm, it sorts and moves the page. So basically we are comparing the both. So we make some some suppositions here. Say the cost of serving the request. Serving the request to v asterisk is A, because as we said in this event, one request comes to B asterisk. So we suppose cost of serving request to V asterisk is A, and cost of serving request cost of serving request to V asterisk by coin flip algorithm is A, and cost of serving request to V asterisk by this optimal algorithm may be B. This is just a supposition. So what is the expected cost of moving the page? So the expected cost of moving the page is E of coin flip algorithm plus the difference in the potential function. So this is equals to the probability the probability of moving the page no sorry, this is just not this, it's just yeah. So the cost of moving the page is expected value for C coin flip algorithm is equals to probability of moving the page into the cost of the page into the solving cost, that is A. And probability of moving the page is 1 over 2D into D into A, it is the solving cost, and DD goes out and it's half A. Now so after getting this, what we want to find is what was the potential before, the original potential. So the original potential was phi equals to d 3d into the, so we already said, okay, the potential is 3 into d into this PCF, that is PCF and POPT, and the distance between PCF and POPT is C, so it's the d distance between CF, PCF and POPT. This is equals to C. So it's 3D dot C. And what's the new potential? So let's say new potential be phi dash, and it is equals to the, so it is a little bit complex, so the new potential would be probability that page is moved into the cost of serving to P OPT if page was moved to V asterisk. So one cost would be, for example, the request came here, so we have two options. One option is either to move the page here and another is not to move the page. So if we move the page here, then the cost we have to find it has some expected cost, and if we don't move the page, then we have some expected cost, because we suppose later the request will come here. So we'll say, okay, if we move the page, then the expected cost would be the cost of serving the page if the page was here, and if we didn't move the page, then the expected cost would be cost of serving the page from here, because we didn't move the page. So plus, so it's again probability that page is moved into the cost of serving to POPT if page was not moved to V asterisk. So this is equals to, so what is the probability of page to be moved is 1 over twice D. Then the cost of serving the page if page was moved to V asterisk was 3 into D into B, because if page was at V asterisk, then we'll need, so cost of serving would be B, because the weight of this edge is B. And if page was not moved, then it would be 2D into 3 into D into C. So if the page is not moved, then cost would be exactly the same as the old potential. Or if you just see here, then it's distance between P and C is C, so we write C, or just say it would be same as the old potential. And so we get this now. So we have to find what is the expected change in potential. So expected change in potential E phi theta equals to E, so new phi minus the old phi. So delta phi is E phi minus the old phi, and so we already know what is the phi, value of phi, and the value of this phi dash is this. So it would be equivalent to 1 over 2D into 3dB plus 1 over 2D into 3dC. That's what we got from here. Oh, sorry. I made one mistake. Probability that page is moved into the cost of serving the page if page was moved, plus the probability that page is not moved, okay, and the cost of probability that page was not moved. So it will be 1 minus, so it's 1 into 2dB plus 1 minus 1 by 2d. Therefore it would be 1 minus here also. Yeah. So this is the value of phi prime or phi dash minus the old potential, that is 3dC, because we have the old potential as 3dC. And this gives you something like B minus C, which is just some elementary calculation. Okay, now we have this delta phi. So we plug in into this expression, that is expected value of coin flip algorithm plus the change in potential. So we just plug in, and what we get is so the value for this is expected value for this is the cost of moving plus cost of serving plus the expected value of FIDES, which we just got. And so cost of moving is, as we said, cost of moving is A. Yeah, so here we said cost of moving is A by config algorithm. So we just say, okay, cost of moving is A plus cost of serving is half A, because we get it from here. So this is the expected value for cost of serving, that is half A. And yeah, plus it's the FIDES, or this is, you can assume this is the expected value of cost of serving, CF, or something like this. And this is half A plus 3 by 2 B minus C. This is from here. So this is FIDES or phi prime. Then it is 3 by 2 A plus B minus C. And from the triangle inequality, what we can say is, let me show you the figure. So this forms a triangle. In triangle, if you add two sides, then it should be greater than the third side. Or you can also say A minus C is less or equals to B. So we apply this triangle inequality, then it would be less or equals to 3 by 2, A minus C is less or equal to B, so we just say B plus B, which is equivalent to 3 by 2B equals to 3B. And if you see, we said the cost of serving to V, cost of serving request by OPT by optimal algorithm is B, so it can be said as 3C OPT. Hence we prove for the first part. So for the first part we can finally write E of CF plus is less or equals to 3 into C OPT. So this is what we do prove for the first part, and also we have to prove same thing for the second part. Now the second event, that is event 2. What we did was optimal algorithm optionally moves the page. So here optimal algorithm only moves the page. Yeah, so what is the cost of coin flip algorithm? So it is doing nothing, so we just write 0. And what is the cost of optimal algorithm? Basically it is moving the page, so it is D into the cost of moving the page, the cost of the edge. And let's make a figure before this. So let's say this is the event 2 and this is the condition of event 2, and this is the point for coin flip algorithm, and this is the pointer node for optimal algorithm, and this is the new node where we want to send. So this is so if this is E, then the cost would be cost of optimal algorithm would be the D, that is the cost of moving a page, plus the weight of the edge, that is E, so it's DE. Okay, now we have to find what's the value for the delta potential, that is the change in potential. So it is equal to new potential function minus old potential function. And what is the new potential function? It is, so by the definition of potential function, it's 3 into d into the distance, and here in case the distance is p new opt minus pcf, and for all it's 3 into the distance between p opt comma pcf. Yeah, then now it's the straight, so it's d into, so p new into popt, p new popt is here and cf is here, and it's d minus the old potential, and the old potential is 3d, and so this edge is c because it's opt to c, cf, and it's c, and or it is equals to 3d d minus c, and using the triangle inequality, so d minus c would be less or equals to e, so this is less or equals to e using the triangle inequality. Then therefore finally we have this expression is less or equals to, so we know the value of this is 0, because in second phase we don't do anything. Yeah, from here it's 0, and the value of this is less or equals to 3de, which is equals to 3 COPT, because this is the OPT value, optimal value. Hence for second event also we prove the same, therefore we finish the proof. Hi guys, there has been a small mistake, so this is not the correct notation. The expected, so this is just half a is just the expected cost of moving the page, and we plug in this value later here, and here the the overall expected value for this is from the definition we say okay, it's the cost of moving the page plus the solving the page, and so this is cost of moving the page and this is cost of solving the page. Okay, so why it is a, because the solving the cost of solving depends on the weight of the edge, and from the figure we had it's a